The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, today we're going to do some crossover between two kinds of data structures, memory hierarchy data structures and geometric data structures. And this will be the final lecture in the memory hierarchy series at the end of Cache Oblivious. So we're going to look at two-dimensional geometric data structure problems, both offline and online. So our good friend orthogonal 2D range searching, which we spent a lot of time in a few lectures ago, we will come back to and try to get our bounds good even cache obliviously. And so instead of log n, we want log base b of n, make things interesting. And the batched version is where you're given a whole bunch of rectangles and a whole bunch of points up front, and you want to find all the points that live in all the rectangles. So that's an easier version of the problem. And then we'll start with that, and then we'll go to our the usual online version where you have queries coming one at a time, rectangles coming one at a time. The points are pre-processed. Will be static. And to do the batched, we're going to introduce a new technique called distribution sweep, which is a combination of the sweep line technique we saw back as we use persistence to make a sweep line thing into a data structure thing. But we're just going to use the algorithmic version of that, plus a cache oblivious sorting algorithm. So we'll finally do cache oblivious sorting and optimal n over b log base m over b of n over b, using a particular algorithm called lazy funnel sort, which you can actually also use to make another kind of cache oblivious priority queue, but we won't get into that. And so by combining those two things, we'll get a kind of divide and conquer technique for geometric problems that lets us solve the batched thing. And then we'll use completely different techniques for the online thing. So for starters, let's finally do cache oblivious optimal sorting. I'm not going to analyze this algorithm because it's just an algorithm, not a data structure. And also because the analysis is pretty close to the analysis for priority queues we did last class. So funnel sort is basically a merge sort. I mentioned last time that in external memory, the right way to do, or a right way to do optimal external memory sorting is an m over b way merge sort. Cache obliviously, you don't know what m and b are, so it's hard to do m over b way merge. So instead, you basically do n way merge. Not quite n way, I can't afford that, but it's going to be n to the 1/3 way merge sort. And the big question then becomes, how do you do a merge? And the answer is with a funnel. And so the heart of the algorithm is a funnel. So if you have k-sorted lists that are big, size k cubed, then you can merge them in basically the optimal bound. So k funnel, k-sorted lists, total size k cubed, number of memory transfers to merge them is k cubed over b times log base m over b of k cubed over b. There's a plus k term, and when you plug this into an actual sorting algorithm, you need to think about that, but it's not a big deal, as long as usually this term will dominate. Okay, so let me show you how a funnel works. We're just going to go through the algorithmic part, and I won't analyze the number of memory transfers. I'll draw this here. So we're going to have the inputs down at the bottom of this funnel. So they have some data in them. There's k inputs down here. Total size of all these is theta k cubed. And then at the top here, we have our output buffer. This is where we're going to put the results. And this will have size k cubed. Maybe we've already done some work and we filled some of it. Okay, the question is, what do you put in this triangle to do the merge? And the obvious thing is recursive triangles. Recursion is like the one technique we know in cache oblivious data structures. So we're going to take square root of k funnels and just join them together in the obvious way. So just like Van and de Boas layout. Except, didn't quite leave enough room here. In between the levels are buffers. There's a buffer here between those two, between the nodes of this funnel and the nodes of this funnel. Okay, these buffers may have some stuff in them at any moment. Okay, and the big question is, how do you set the buffer size? This is the key step. And the claim is each buffer we set to a size of k to the 3/2, because the number of buffers is about square root of k, because there's one per leaf of this funnel. And a k funnel has k inputs, so a root k funnel is going to have root k inputs here. And so the total size of all the buffers is k squared, which is not too big. I'm not going to go through the recurrence, but if you add up the total size of this thing, it is linear size in the output, k cubed. I think also if you don't count the output buffer, it's linear in k squared, if I recall correctly. We're not too concerned with that here. Just overall, once we have k funnels, funnel sort is just going to be n to the 1/3 way merge sort. With an n to the 1/3 funnel as the merger. We can only afford up to n to the 1/3 because of this cubic thing. We can only merge if we want the sorting bound n over b, log base m over b of n over b. We can only afford k being up to n to the 1/3, so that's the biggest we can do. So it's a recursive algorithm where each of the merging steps is this recursive data structure. Now this is really just about layout. I haven't told you what the actual algorithm is yet. But it's a recursive layout, right? You store the entire upper triangle, then each of the triangles, somewhere you put the buffers. Doesn't really matter where the buffers are. As long as each triangle is stored as a consecutive array of memory, we'll be okay. And now let me tell you about the actual algorithm to do this. It's a very simple, lazy algorithm. So there's a whole bunch of buffers. If you want to do this merge, really what you'd like to do is fill this output buffer. So you call this subroutine called fill on the output buffer and say, I would like to fill this entire buffer with elements. Precondition, if you're going to do a fill, right now the buffer is empty. And then at the end of the fill, you'd like this to be completely full. And how do you do it? Well, if you look at any buffer, partially filled, whatever. You look right below it, there's a node in this tree. You recurse all the way down. In the end, this is just a binary tree with buffers in it. So it's going to be, there's a buffer, then there's a node, Then there's two children, each of which is a buffer. And then there's a node below that, whatever. Okay, so how do I fill this thing? I just read the first item, or the beginning, the smallest item for each of these, compare them. Whichever's smaller, I stick it here. It's just a regular binary merge. Which is kind of cool. You've got two arrays, you want to merge them, stick the results here. So that's how we do fill. Binary merge of the two children buffers. Until we're full. But there's one thing that can happen, which is that one of the child buffers might empty. What do we do then? Recursively fill it. That's the algorithm. Very simple. The obvious lazy thing to do. Do a binary merge. This is going to be nice because it's like two scans until one of these guys empties. And then you pause this merge and then say, okay, I'm going to fill this entire buffer, which will recursively do stuff until it's completely full, or I run out of input elements, whichever comes first, and then resume this merge. Question?
Are there more than two child buffers?
Should only be two children buffers. Because question is, are there more than two? This recursion of the root k and root k child triangles of size root k is exactly the recursion we did in a binary tree. I didn't say, but underlying this is a binary tree. The only difference between this and a Venn to Bose layout is we're adding these buffers. So I intended to draw this as binary. It's a little hard to tell because I didn't draw the base case, but it is indeed binary tree in the end. Okay, other questions? So that's the algorithm, and as I said, I'm not going to analyze it, but it's the same kind of analysis. You look at the threshold where things fit in cache or don't, and argue accordingly. It's pretty hand-wavy. What I want to get to is how we use this to solve more interesting problems than sorting. Sorting is a little bit boring. So let's go to batched orthogonal range searching. And in general, this technique called distribution sweep. So the idea with distribution sweep is that not only can we use this cool funnel sort algorithm to sort, but we can think of it as doing a divide and conquer on the key value. And in this case, we have two coordinates. We're going to use the divide and conquer on one of the coordinates. And where we have some flexibility is in this binary merge step. We're doing this binary merge, and normally it's just you take them in, you spit it out here, you take them in, you spit it out here. But if that's the min of one particular coordinate, now you've got to deal with some auxiliary information about the other coordinates. So in general, you're merging two sorted things. If there's other geometric information, you can try to preserve it during the merge. As long as you can do that, this is sort of the conquer part, or the combined step of divide and conquer. You can do a lot. It's a powerful technique, turns out. It's by Brodel and Fagerberg. It's in the early days of Cache Oblivious. It's the first geometric paper. Fine. So replace, or say augment, the binary merge which is in the end the only part of the algorithm other than the recursion. So it's the only thing you need to do to maintain auxiliary information. Okay, that's the generic idea of distribution sweep. And distribution sweep has been applied to solve lots of different problems. Batch orthogonal range queries is one of them. Generally, you've got a bunch of orthogonal segments, rectangles, points, and you want to compute how they intersect. The sorts of problems that can be solved here. Also weird things like I give you a bunch of points and I want to know for every point what's its nearest neighbor in Euclidean sense. That can be solved. But I like orthogonal range searching because it's the closest to a data structure problem. That's a problem we've seen. So the actual batched orthogonal range searching is you're given n points and n rectangles, and you want to know which points are in which rectangles. Okay, that's the general problem. So normally we're given the points first, and then we're given the rectangles one at a time. That's what we've solved in the past. It's what we will solve later. That's the online version. The batch version is I give you a whole bunch of queries I want to know simultaneously, and we're going to achieve the sorting bound n over b log base m over b n over b plus size of the output over b. And this is generally the optimal bound you could hope for. It's not obvious you need the log, but I think for most problems in external memory you need this log. It's hard to beat the sorting bound. And then once you pay the sorting bound, this is the optimal linear time to just write down the output. Now, this problem can be solved. Give me all the point rectangle pairs that result. I'm not going to solve it here exactly. We're going to solve a slightly different version. Or in general, whatever. Let me tell you about another version of this problem, which is a little bit easier. Then I'll sketch how we solve that problem. So remember, we've talked about range reporting and also range counting. You just want to know the number of answers. Here's something in between. You want to know for every point how many rectangles contain it. Okay, in particular, this will tell you for each point, does it appear in any of the rectangles in the set? It'll tell you how many. And this is actually necessary as a first step, because one of the hard parts in solving these kinds of problems, reporting problems, is that the output could be big. We know that's always an issue. But with Cache Oblivious, it's a big issue, literally, because space is important. You can't afford to put space anywhere. If I want to put, if in here, if these buffers have to get much bigger in order to store those answers, then life is kind of tough, because then this data structure gets too big, and then my analysis goes out the window because things that used to fit in cache no longer fit in cache. The analysis I didn't show you. So it's an issue. So for starter, so the first step of this algorithm is to first figure out how big those buffers have to be so that we don't have to allocate them too large. And to do that, we need to basically count how many answers there are, and this is what we'll do. And to do this, to compute these values, the answers aren't very big. I mean, these answers are just single numbers per point, so it's no big deal. Okay, so here's what we do. Sort the points and the corners of the rectangles by x coordinate using lazy funnel sort. Nothing fancy here. No augmentation. Regular old sort. Then, this will be useful later. Then we're going to divide and conquer on y. via distribution sweep. And here, our binary merger is going to be an upward sweep line algorithm. So let's talk about that sweep line algorithm. Okay. So we pre-sort our points by x. And now, if you think about the merging step, what this means, it's confusing. We're trying to sort by y. We were in a certain sense, but we're always going to be sorted by x because we did that up front. So the picture is going to be something like this. We're in a slab. There's going to be the left slab. So here's the binary merger. There's the L points and the R points. The L points are going to be in a particular x interval. The R points are going to be in another x, in an adjacent x interval corresponding to this tree picture. And then we have these points, which they overlap in y because the whole point is we're trying to merge by y. Okay, we also have some rectangles, and their corners are what we have represented. Probably should have used colors here. Something like this. Okay. And now we're given essentially, we have whatever we want on the points and corners in here. We have whatever we want in the points and corners in this slab. Let me add a little bit of color. These lines. And now we want to merge these two things. And merging here is all about counting how many rectangles contain each point. Now, we already know how many points over here are contained in rectangles that are over here. So we've presumably already found that this point lies in this rectangle. We've already found, I guess there's no points here, already found that this point is contained in this rectangle. Okay, because these corners were in this slab, and so let's say every corner knows the entire rectangle. So when you were processing R, you saw these corners, you saw this point, somehow you figured that out. What we're missing are things like this rectangle, where none of the corners are inside R. So R knew nothing about this rectangle, and yet it has points that are contained in it. Similarly, there are these rectangles that completely span L. They go, and so therefore none of the corners are inside L, but we need to know that these points are in there. Those are the only things that will be missing at this level. Now there might be there might be other rectangles that completely span L and R. Those will be discovered at higher levels, not here. So it's a little bit awkward to check that this will actually find everything, but it will. So to figure this out, we have to, when we're merging L and R, see L knows about this rectangle because it sees these points. We want to keep track, as we sweep upwards, we want to realize that these points are in a big rectangle here. Whereas they weren't discovered in L, they weren't discovered in R. To do that, we maintain a number. As we have a horizontal line, we're sweeping up. We want to maintain the number of active rectangles. Active means that it's currently being sliced by the sweep line, that have left corners in L and completely span R. So that's these guys. So that's easy to do. As we're merging these points, so each of them has been sorted by y. Now we're doing a merge, so we're considering all the corners and all the points in increasing y-coordinate as we do that binary merge. So whenever we visit a left corner of a rectangle, a lower left corner, we say, oh, does this rectangle go all the way across? This one does not. By the time we get to here, this one goes all the way across R, and so we increment CL. And when we get to the upper left corner, we decrement CL. Say, oh, that rectangle's over. So it's very easy to do constant time, but it's only going to be 1 over b memory transfers per one of these because it's a nice cheap merge. And then symmetrically, we do CR. It's the number of active rectangles with the right corners in R that span L. So that's this guy, CR, I guess, and this guy is CL. In general, there might be a lot of them, so you count them. And then the only thing we need to do is whenever we encounter a point as opposed to a corner, because we're storing them all together, we add, I got this right, CR to its counter. We want to know how many rectangles contain that point. And so, for example, when we see this point and CR is currently 1, then we know that this point appeared in some rectangle that spanned L. So we increment this point's counter. Similarly, when we see these points, CL is positive, so we increment these guys' counters by whatever CL is. So there's a symmetric version in R. We add CL. Probably should have called them the other names, but anyway, CL, CR, it doesn't matter. CLRS. Question?
The bottom is the x-axis, right?
This is the x-axis, yeah.
So are we dividing and conquering on x?
It does look like we're dividing and conquering on x. I think you're right. Sorry. For some reason I thought it was y. You're right. So it's a funny thing. We're pre-sorting by x, yeah, which is what's getting us. Thank you. That's much clearer now. In my mind, I was like, well, there's something weird here. We're pre-sorting on x, and then we're just sticking these guys down here, so like evenly dividing them into lists. Or I guess actually we're doing our where is it? Funnel sort, the merge sort. Things have already been sorted by x, but now we're merge sorting again. And this time when we merge, we carry along this information. So they're both in terms of x, which is kind of funny. So another question?
Sorry. Is it important that we do the upward sweep in order?
The upward sweep, yeah, we have to do the points in order by y.
So is it just we wanted to sort by y and then divide the counts on it?
Oh, I'm so confused now.
Because in the notes it says x and then y.
Yeah, I know in the notes it says y. It used to say x. I believe we're dividing and conquering on x, but we're sorting by y, and that's the confusion. I'll double check this. But in order for this sweep to work, so it's like you first sort by x, we are in some sense doing divide and conquer by x because we did this sort by x. But the merge sort is on y. It's right, it makes more sense. If you're already in x order, sorting isn't going to learn you much. Isn't going to teach you much. So first you sort by x. Things are nicely ordered by x, so we get these nice horizontal slabs in the decomposition. But now when we merge, now we're going to sort by y, so we're going to reorder the points, and that's what lets us do the sweep. And we are, in the end, merging all these points together in y order. And as we do it, then we get the information we want about rectangles and points. Okay. This is why I wanted this to be both x and y. But really, the divide and conquer is happening on x, but we are doing a merge sort on y. Finally clearer. Thanks for helping me resolve this. This is a new lecture, as you may have guessed. So still working out some kinks. But I really wanted to introduce this lecture because the next thing we're going to cover, which is a way to do orthogonal 2D range searching cache obliviously, is super cool. It's like one of the craziest things there is. So, at least in the cache oblivious world. Any other questions before? Oh, I should say a little bit more about this. We've now solved this first step, so to speak, which is figuring out the output size, counting for each point how many rectangles contain it, which is an interesting problem by itself. That's the range counting problem. You can also use it to figure out at this level, at this merging step, how many things will be output here. How many new outputs are there? How many points in rectangles are there? It's essentially just the sum of all those things. Okay? So you can count the number of outputs per merge. And so then there's a natural strategy, which is you build a new funnel structure where these buffers have the right size. You've pre-computed what all the sizes need to be. At every merge, you know how many things are going to get spit out here. So you could allocate that much space, and that will be a kind of decent merge chart. Because I haven't done the analysis, it's hard to get into detail about this. But it will not be optimal, unfortunately. To actually make it work, you end up having to take this tree, carving it into subtrees of linear size. So normally, the whole thing is linear size, everything's fine. And where the analysis breaks, essentially, is if you have a giant buffer because one of the outputs, potentially the output size here is quadratic. And so the overall thing might be superlinear. And so when you have a superlinear buffer or a bunch of very large buffers that sum to linear size, you essentially need to carve that tree, which you do by a recursive carving of the tree, so that each of the trees has linear size. Then you apply the analysis to each of the trees separately. You store them consecutively separately. Each of them has good optimal running time, and then the combination does. That's the hand-wavy version of how to do actual range reporting with endpoints and end rectangles. If you're interested in the details, read the paper. It's just a little bit messy, and especially when you don't know the analysis. But I want to move on to online orthogonal 2D range searching, because it's the hardest and coolest of them all, unless there are more questions. All right.
So we did the range counting problem in detail and translate the actual
Exactly. At this point, if you believe in funnel sort, you should believe that range counting is easy to do. And I've just hand-waved the range reporting part. Are you scribing? Is that why you ask? That's where we stand. The next thing we're going to do is regular range reporting, regular online stuff. So this is orthogonal 2D range search. And we spent a couple of lectures on 2D and 3D range search, all this crazy stuff with fractional cascading and so on, and the layered range trees. We're going to use some of those techniques that we built there. And in particular, you may recall there was this idea that if we have a bunch of points, regular 2D range searching is I give you a rectangle, give me all the points in the rectangle. Fine. Our goal is to achieve log base b of n plus output size over b. That's the new optimal bound. This is how long it takes to do a regular search in one dimension. So if you have output size, whatever. And we'll probably be able to do range counting, but I won't worry about it here. We'll just think about range reporting. If there's this many points, output them all in that much over b. This is what we call a regular range search, but I'm going to distinguish it and call it a four-sided range search because a rectangle has four sides. But you could think of the other versions, and we actually did this when we were doing the 3D problem. So if these are two rays and an edge, this you might call a three-sided rectangle. And you can go all the way down to two sides. Hard to go down to one side. Here's a two-sided rectangle. It just has two rays. Okay, as you might expect, this is easier than that. And if I recall, in 3D, we ended up doing this thing in linear space with this fancy, first you do a search on the left coordinate, and then you just walk. We'd subdivided with fractional cascading so that every face had constant size. And so you could just walk, and each step you'd report a new point, if you may recall, for this kind of two-sided thing. First you search for this, and then you basically just follow this line until you found this point, this corner. So in this we could achieve in linear space, logarithmic time. This one we needed n log n space. Actually, the best known is n log n divided by log n. That was, but we could do n log n using range trees. And we got down to log n time using log n query time, n log n space using layered range trees. Okay, that was the internal memory, regular algorithms. Am I missing an m over b? No, this is log base b of n, not log base m over b of n. Yeah, it's good to ask. When we're sorting this kind of thing, we get log base m over b. But when you're searching, the best you can do is log base b. We actually proved a lower bound about this in the first memory hierarchy lecture. Because if you're looking at b thing, I mean, when you read in a block, because this is online, you read it in a block, you can only learn where you fit among b items. And so the best you can hope to achieve is log base b of n for search in one dimension. So this is a lower bound for search. When you're doing batch operations, then you can hope to achieve this stuff, which is a lot faster. Then it's like 1 over b times log base m over b of n over b. Okay, so in a certain sense, this is slower than the batched operations, but it's more online, so it's a trade-off. Okay, so for all of these problems, we can achieve log base b of n plus out over b. The issue is with space. Maybe I'll do sort of regular RAM algorithms versus cache oblivious. So we've got two-sided, three-sided, four-sided. And for two-sided, I believe these are the right answers. Log n over log n. We haven't actually seen this one. And cache oblivious, here's what we can do. This is with optimal query times. And this is all static. Okay, and if there's time, I'll cover all of these. So they're not perfect. These two were off by a log factor. But not bad. Pretty good orthogonal 2D range queries. And really the coolest one is this one. This one blows my mind and every time I see it. So let's do it. We'll start with two-sided, and then we have existing techniques once you have two-sided to add on more sides. You may recall from the 3D range searching lecture. So we're going to use those techniques and refine them a little bit to get that log factor. But you may recall way back when, at lecture 6 or so, that we had a technique. Once it was two-sided, every time we added a log factor in space, we could add another side. The hard part was getting up the number of dimensions. Then the easy part was turning half-infinite intervals into regular intervals. So it's once we have this, it's easy to add a log, add another log. Just with a bit of sophistication, we can save a log factor. Okay, but let's do two-sided. This will be the bulk of the lecture. This is a paper by Arga and Zay in 2006. All right, so we want to do, I'm going to assume that they are this kind of quarter plane queries. So less than or equal to x, less than or equal to some y coordinate. We want to know all the points in that quarter plane. So here's what we're going to do. It's all static. We're going to have a Venom to Boas layout, so binary tree, on the y coordinate. So this just stores all the points sorted by y. Okay? So if you want to do this query, you search for that value of y. Then each of these positions, in between two keys in here, has a pointer to an array. The array is not sorted by x or y. It's a weird, very weird thing. And then here's the algorithm you follow. When you follow this pointer, you go here, you walk to the right until you find a point whose x coordinate is too big. It's bigger than x. I should probably call this x2, y2. So first you search for y2 here in this thing keyed by y. Follow the pointer. You look at all the points that have x coordinate less than or equal to x2. Those are the ones you want. Once you find a point whose x coordinate is bigger than x2, you stop. And then you report these points. And it's not quite so simple because some of these points might be duplicates. You have to remove duplicates. That is your answer. To me, this is an insane idea. I would never imagine this to work. But the claim is you can make this array have linear size. That's the hard part. Make this, the amount of stuff that you have to traverse here, be linear in in the number of points that are actually in this range. So you don't have, you are going to do a little bit more work because there are duplicates in here, but only a constant factor more work. And yet somehow you've taken this two-dimensional problem and squashed it onto a line. You did one search at the beginning, which costs you log base b of n. Then you do this linear scan, and you get the right answer magically. I don't know how they thought this would be possible, but magically it turns out it is possible. It's kind of a breakthrough in cache-oblivious range searching. It was known how to do this for external memory a lot easier. For example, you can do it with persistence. But this is a much cooler way to do two-sided range queries. All right, so I've explained the query algorithm. Well, the big thing I haven't explained is how to build this array. And yeah, maybe I'll write down the things we need to prove as well before we get there, so you can think about them as we're writing down the algorithm. First claim is that this algorithm, which just decides to stop whenever it gets an x coordinate that's too big, actually finds the right answer. Finds all points in the range that we care about. Second thing is that the number of scanned points, the length of that step here, is order the size of the output, the number of actual output points. So we don't waste time doing the scan. And the other thing is that the array has size order n. That's sort of the biggest surprise to me. So those are the three things we need to prove about the algorithm, which I will now tell you. Okay, before I can define how this array works, I need to define a concept called density. So, if we look at a query, there's sort of two things that could happen. The good thing for us would be if, get this right, the number of points in less or equal to x star is at most alpha times the number of points in the answer. Okay, star means no restriction on y, minus infinity to infinity. This would be good for us because it says, I mean, ultimately what we're trying to do here is do a scan in X. So if, yeah, what's the right thing to do here? Then for this particular y coordinate, we could just basically start at the beginning of the array, start scanning, and just report all the points that are actually in our range. Sorry, I need to also here potentially throw away points that are not low enough. So the answer is contained in here, I should say. To throw away duplicates, you have to throw away points that are not in the range less or equal to x comma less or equal to y. Still, we claim the number of scan points is proportional to the output size. That's what we need. So if this held for every query, we'd be happy. Start at the beginning, scan, and as long as this alpha is some constant, it's going to be a constant bigger than 1. Then the number of points in the answer is proportional, the number of points we had to scan through is proportional to the number of points in the answer, and so we're done. Okay, so this is the easy case. We need to distinguish it. Otherwise, we call this range query sparse. And those are the interesting cases. So nothing deep here, but we're going to use this concept a lot.